All right, so our last topic is just one that's really, in here so that you guys can see another way of approaching hypothesis testing. It's not the way I like to do hypothesis testing, but others, instructors or other disciplines may consider using rejection regions as opposed to p-values. So this is an alternative. So I'm just showing it to you in case you end up in another stats class or you have to use statistics for some other reason you want to know what this is. So our first example, a random sample of n observations is selected from a normal population to test the null hypothesis that mu is equal to 15. Specify the rejection region for each of the following combinations of the alternative alpha in sample size. So this really comes down to, in the day and age, especially before technology was so easy to use, we had our tables. The tables are a little convoluted to use for the p-values, right? That range can be confusing for a lot of students. That's why I walked through that 4 different times, and I'll probably end up walking through it again next week. So let's just draw out what's happening. So this first example, ooh, that is not the pen I wanted. This first example, we're testing whether or not mu is equal to 15, right? That's our null. So we're going to center our normal distribution at 15. We have an alpha of 0.10, we have an n of 25, but we don't have anything else, right? So we're talking about rejection regions. So rejection regions are basically values of t where we would reject. So instead of looking at this one, I realize now I need to be looking at a t distribution which is centered at 0. What matters here is, since we have the greater than, we're looking at a right-tailed test. And what we want for this right tail, whenever we find it, we don't know what the t is, right? We want this value to be something less than 10%. So we need our t to be something this way. This would be rejecting the null. Anything over on this side would be failing to reject the null because we wouldn't get something unusual enough. So 10% is our bar for unusualness. So we can figure out exactly what that t is because we have the sweet t table, right? If we're going to use the t-table, we need a degree of freedom. And we need an upper tail probability, which is exactly what this gave us. So let's go to our t-table. We needed our degree of freedom to be 24. And we wanted our upper tail probability to be 10% or less, right? Any of these values would also have us rejecting the null. So let's go figure out what our cutoff is for this rejection region. So a t of 1.318 would be exactly at 0.1. And so any t larger than that, right, anything else will put us further down this row and therefore have us rejecting the null hypothesis. So 1.318 is what we want for our t. I can erase this and put in 1.318. So our rejection region would be reject if t is greater than 1.318. And then we fail to reject in any other situation. So if we did a question like the previous one, all we'd have to do is look at our t and go, no, that's bigger, reject the null, instead of going to a p-value and comparing that to the alpha. So it's basically, do you go all the way down or do you sort of meet halfway to do the hypothesis test? So you guys try out the other one. We're now doing a two-tailed test. See if you could draw that picture and think about what the different rejection region is going to be. So hopefully you tried it on your own. We're still talking about a t, so we're still centered at 0. Now, since we have the not equal to, we're dealing with a two-tailed test. And we want the area of those tails to be no more than 0.01, which has got to be split between them. So we need 0.005 in either of our tails. And anything out in this region and this region, we would reject the null. Anything in the middle would not be unusual enough. That would have us failing to reject the null. So we just need to figure out what that cutoff is. And of course, if we're going to our table, we need our degree of freedom, which is 11, and we're on the hunt for this upper tail probability of 0.005. So 11.005, we need something very small, so we need a very unusual t. So our t is 3.106, and again, anything greater than that would be a smaller tail. So that's where our rejection region is going to start. So this is 3.106, which means the other side is negative 3.106. So we will reject if our, and you can use absolute values if I want, if the absolute value is greater than 3.106, or you could split it up into two, where t is greater than 3.106, or t is less than negative 3.106. Either one of those works. So the question then, because what if we had a test statistic of 2.56, how would we decide? So in the first question, 2.56 would fall into our rejection region. So in example 1, we would reject the null. But for example 2, it would fall here into our fail to reject the null. So that's how rejection regions work, in case you're ever dealing with those instead. The reason I don't love rejection regions is they change, the actual values for them change depending on what your distribution is, where p-values always mean the same thing. So whether you're in a z, a t, a chi-square, an f, these other distributions we haven't even seen yet, a p-value always means the same thing, whereas otherwise these values all change and you don't know them off the top of your head, right, like you would for, say, a normal distribution.